So the next talk is by Tobias. So sorry for the redundancy. That's my creativity. There are two DSLs there. So he's going to talk about how to design DSLs with xDSL.
Exactly. So yeah, well, thank you for everyone being here, and thank you for all the previous really interesting talks. So I'd like to talk about really like a compiler framework that we've been building initially in Edinburgh, where Ami is currently, and now in Cambridge, for building DSLs, or for building domain-specific languages. And I'm very brief with the kind of the motivation, but kind of our motivation came from kind of domain-specific languages. We collaborated with the DeVito project, which is a Python DSL for HPC, computational science. And there was this interesting realization that as DeVito became more and more successful, it became more and more a compiler project rather than a kind of HPC project. And obviously, DeVito also was more and more interested in saying not just we can run on GPUs, but really can we run on the latest AI accelerators. And then there was this interesting tension. Does Imperial now want to hire all the like AI compiler experts for the HPC project, right? And so that's how our project started. But kind of the more general question really is how can you build compilers for these kind of very specialized hardware? And in particular, our take on that question is how can you do that in a sustainable way, right? So DeVito had this HPC DSL, implemented in Python, has 3 IRs, applies many classical loop optimizations, and does actually really interesting. I mean, this is now a seismic imaging example, really interesting computations using algorithms like around reverse time migration to get a picture of the ocean ground. What I was deeply excited about is that when I learned that you can use very, very similar algorithms to pretty much get like CT level imaging just from an ultrasound, which I found really cool. But anyway, like this is a very domain-specific application, and they built a compiler internally, right? And it's incredibly successful, right? DeVito is actually a research project that is used at scale in industry just because it's so convenient to use it from Python, and it actually provides the features people need. And at the start of our project, Google had a very similar problem, that they had a framework called TensorFlow, which was quite large, had also different kind of IRs, and then pretty much their solution was to eventually build their own compiler framework. And so some of you may already realize what I'm talking about, and I try to be very brief. So Google at that point developed a compiler framework called MLIR, which had the objective to make it really easy to instantiate reusable abstractions and kind of put them together and then use that to pretty much build your own compiler for whatever domain you want, right? And just to give you a brief introduction of what MLIR really is, if you have a stack language, for example, that you want to optimize, and you want to build a compiler for that language, you pretty much can turn that stack language in an LVM-style IR using MLIR. Looks slightly more verbose, but in the end, what you need is what's called an MLIR a dialect for that abstraction. And in this case, you have a stack dialect where you can push and pop types to your stack, and you have a stack type, right? And the interesting thing, and I think I'd like to be a little slow here, even though that's relatively simple, is that really the key idea is that whenever you have an abstraction, whenever you have a set of operations that somehow interact with, like, can be simplified through certain algebraic properties, sometimes it's actually quite useful to scale that up or to build that in a real compiler framework, just because the tooling around that framework is very useful and powerful to build these kind of things. And then, for example, you can use your DSL compiler to try to optimize these things. Then your stack language might fall away and become more optimized, right? So that's the idea of MLIR. And hopefully I convinced you in a couple of minutes that MLIR is an amazing thing, right? Some of you may believe that this was probably too short to convince the people who don't believe it yet, but maybe you have heard of it. So I was convinced so my objective in Edinburgh now in Cambridge was to kind of use this tool and then research and open source development, teaching at scale with students. I wanted everyone to use MLIR. I found it's amazing. So that was my objective, right? And actually this is kind of, it's funny because I moved to Edinburgh and then there was a little bit kind of, I had to take up a compiler class, needed to teach it. It was kind of an old Java-based course, and I was just like, should I really learn, like update my Java skills to kind of teach that class, or should I just teach MLIR? And then we were really motivated and kind of just really tried to teach MLIR. In particular, we wanted to teach a lot of compiler concepts, but we quickly realized and actually burned one student over the summer on kind of the overwhelming complexity of the actual framework. Right? There's a lot of unrelated tools there. So we realized that just getting started with this framework is really difficult. And so what we built is just actually tailored for students, a framework that is pretty much a deep copy without scientific novelty of MLIR purely in Python. And this kind of minor shift of like implementation language actually made this tool so much more accessible. So we really focus on approachability, accessibility. We try to reuse all the existing concepts already in kind of the production compiler world. And in particular, what I think was quite new is that we made that framework very much interoperable on the like textual IR representation. I have a slight motivation why it makes sense to have many IRs, but I think we go very fast. Over the last 5 to 10 years, there was just a huge explosion in IRs, and kind of we moved away from a linear compilation flow to really an entire DAC of abstraction that kind of gets built by many different domain-specific languages. Matrix multiplication, as a result, can be expressed very directly with like structure and control flow. And as you see, some of these operations, the for loop, the store, are relatively high level in the sense there's a full for loop operation in your IR. You can also have very tailored types, right? Reasoning about high-level multidimensional tensors is quite useful if you target modern AI accelerators. So being explicit and maintaining that kind of information is really helpful if you want to target kind of any hardware that exposes domain-specific expressions at the hardware level. The attributes is also there, but that's not a major thing. But this kind of structured nesting of control flow is what I think makes MLIR quite special. And so then you can really move through abstractions, through your compilation graph, eventually generate GPU code, and that is MLIR, right? And so what we did, what I found quite amazing is next to MLIR, we built up almost like a parallel ecosystem of compilers that feels like MLIR, that does exactly the same thing. So you can actually quite easily transition between these two ecosystems. But sometimes one ecosystem is slightly preferable, right? So if you, for example, belong to the people who, small number of people who have been convinced that MLIR is great, but you didn't try it yet, you could in a couple of minutes try it with xDSL and then get a first impression and then move to MLIR. But the key idea really here was that building compiler sidekicks in general sounds maybe not the most clever idea because you just copy-paste ideas from others, but kind of it's actually quite successful. And there are many use cases where like a different sidekick might be the right tool for you. Let me just go slightly faster to what I want to show you. Like, just if anyone kind of wants to understand, for example, how we implemented the stack language, it's actually relatively easy to define, for example, new operations or new types by just using a couple lines of Python code, right? So in practice, you would probably need to use one of our tutorials or have someone sit next to you. But the main thing is that within maybe an hour or something, you could start building your own abstractions versus like having to spend a day or a week kind of getting to know a relatively large, complex framework. You can also quite easily implement rewrites. And overall, what I found interesting is that obviously Python is slower, but actually not so much slower, right? And in fact, installing our framework, downloading it, or even recompiling a file is relatively competitive, if not even faster than a kind of a large-scale C++ code base. So now I made the case for xDSL. Let me show you what you can actually do with that. And that kind of relates because I think many of you build DSLs, build domain-specific concepts. So I want to give you like two examples. One example where we built something with xDSL, and one example where we went a little bit crazy and built yet another sidekick. So what we actually did then ended up doing with Imperial was we took DeVito, the OpenEarth compiler, and Cyclone, which is a climate simulation, and which previously all of these were completely disjoint projects with their entirely disjoint individual compilation stacks, and we analyzed them and saw can we find synergies, right? So in particular, all of them were monolithic domain-specific languages. They were successful in their own community. They had delivered high performance. They were relatively productive to develop. They were portable. But they also had plenty of compiler optimization inside that were all independently developed and maintained, right? And so what we did is really like we merged all these projects together to make sure that they share a common set of abstractions. And then over time, we hope that there will be a lot of synergies from reusing shared concepts. All of that was done around actually using MLIR style abstractions implemented in xDSL. So we have a stencil abstraction, we have a Fortran abstraction, we have GPU, MPI abstractions, even hardware synthesis abstractions, and a lot of other abstractions. And what's interesting is that it's really a kind of a relatively modular accessible compilation stack. This was built around xDSL, extending the general idea of what we had as a kind of a stencil dialect in the OpenEarth compiler initially. Then we added, and I think what I'm particularly proud of, we actually built an entirely new MPI abstraction, which we meanwhile upstream to MLIR. So if any of you is interested in doing kind of large-scale HPC code generation, I can let you know that there's already an abstraction available now that you can use and that kind of translates to linkable code that you can run on an HPC cluster. And then we pretty much built the entire flow from our stencil abstraction to a distributed memory high-level abstraction to low-level MPI, right? And I guess that's one of the lessons across DSLs. MPI is such a general abstraction, so maybe it really makes sense to share these things. Performance-wise, I think we were quite happy with, like, we didn't fully match DeVito's performance yet, but our scaling behavior was very, very sensible. And in fact, for certain GPU kernels, our code was already faster, right? And this pretty much, we're just at the beginning. We're just getting kind of these codes optimized. So hopefully there's more to be done. Same thing for Cyclone. Scaling here is not as good, but wasn't actually quite bad. And some of the performance numbers for these like weather codes actually improved quite a bit. So now, this was kind of an end-to-end project. Actually took like several years to kind of build this entire project. But we're now at a stage where we really believe like DeVito built on xDSL actually starts to be quite a sensible like end-to-end software product in a way. And now I wanted to show us like a kind of a slightly crazy sidekick that we built. And we called it Lean MLIR. So it's, previously I made the case that it makes sense to re-implement compiler frameworks again and again in different programming languages. So we kept doing that, and this time we chose Lean as an interactive theorem prover to provide a formally verified implementation of MLIR, right? And the very same benefits apply. You can copy-paste your code, you can copy-paste your IR, you can write transformations in one framework and then in the other. And so depending on your use case, right, if you care about productivity, maybe you want to use xDSL. If you care about correctness, maybe use Lean MLIR. But I guess I want to expand on the case, like building sidekicks, so building like kind of almost like an ecosystem of compilers really may make sense. And the main idea is that there's CompSet, which is a really impressive project, end-to-end certified, but also painful to develop, and in fact, really as a disjoint development, right? If you don't care about airplane security, you might not want to become a CompSet developer. That is maybe overly extreme, but roughly, they're very disjoint communities. But interestingly, in the LVM community, there was actually an incredibly successful formal methods project, which is called Alive. And this project is referenced weekly in the LVM commit logs, not because the LVM community cares about correctness, but because they care about, they are lazy. They want to save code reviewing time. And so it's really helpful to have an automatic tool that can assert correctness for certain people rewrites. And that's where like the LVM developers keep using Alive. I think they have over 800 commits which reference Alive. And so Alive is great, but it only works on bit vectors, and it's also not certified. And so our question is, can we use Alive or an Alive-style workflow kind of to trick the LVM developers into starting to use formal methods at scale at even kind of more formal and maybe even larger level? And can we use that also to maybe reason about non-bit vector types? And the first problem we saw is that MLIR obviously doesn't have formally defined semantics, but kind of semantics and documentation code, comments, and conversations. And so we actually have two projects, one where we use an SMT solver purely, and one is our Lean MLIR project where we kind of go for maximal expressivity, and that's pretty much how it looks like, right? So this is a slide where we need to go a little bit slow, but it's actually not very complicated. So if we want to prove correctness of that an add is the same as an XOR for 1-bit type, in our framework, we pretty much just complete the MLIR code. And as you see, we have a full syntax embedding of MLIR and Lean. So you now have a definition of your source statement and your target statement, plus all the like semantic data structures that are related to the syntax. And then the only thing you need to prove is pretty much this proof. So we need to check that source and target have a refinement relationship. And our framework can pretty much simplify away all the like SSA properties, all these complexities, and just leaves you with a bit vector level proof obligation, right? And so this particular proof obligation, Lean can solve automatically. Slightly more complicated ones you might need to step in. But the key from that slide really is that, and I think that's something interesting. We moved this Alive, we moved this Alive framework pretty much a full interactive theme improver, and now we connected the MLIR community with the interactive theme improving community, and people can collaborate on these kind of proofs. We are working on making SMT level decision procedures automatic in Lean, and there are type definitions, and in particular, you can now start using that framework to verify lowerings or rewrites on an abstraction level. We did that for big vectors, for loops, and for fully homomorphic encryption. And that's the end of my talk. If you want to know more about xDSL, check it out. And thank you for all the other collaborators that worked with me on xDSL.
We have time for 1 or 2 questions in the meantime.
How much of my DSL compiler does xDSL want to eat? More or less, like one key thing that's always ambiguous to me when I see this is, okay, I see I can define an IR with this tool. I see there are mechanisms for defining transformations, but this MPI dialect kind of raises a question for me, which is, did it start out with this as something you defined within the project and then eventually push most of it into MLIR for various reasons? Or is it somewhere in between? And if I was defining something, would there be some point at which I would say, oh, I can no longer continue to do what I need to do if I express things in this framework? Like, where should I make that point of trade-off? Why did the MPI, like how much of it should it eat? Where should I be doing things in Python or in the framework or in MLIR?
Right, so I guess let me just briefly talk about like how does that work with I mean, MLIR is so generic as a data structure that you pretty much can express anything in it. And I think you should, because the main benefit of MLIR is not actually like beyond being the specific framework, and I think that's what the case I wanted to make with these sidekicks, is actually not even the framework, it's the fact that you pretty much completely eliminate the thing you have a project, I have a DSL project. If we want to connect our projects, the first thing is different programming language, different programming language, different implementation, data structures. Let me help that. So the first thing is you have different programming language. No, that doesn't work. Let me do one after another. I mean, I'm clearly not. Hello? So I'm clearly not an expert of multitasking. But let me answer that briefly, and then we get the stage for our next speaker. So the main point is that it eliminates any kind of like engineering efforts you need to do to connect frameworks before you start discussing the actual abstractions. And if that eliminating that is actually the one thing that you can like with automation, with tooling, really streamline. Discussions about abstractions, how much to share and all these things, I mean, that's what you need still to do. And I think our like Lean MLIR framework is an example that, for example, if you want to formally verify your DSL compiler, if you implement it in Python and you have like a completely homegrown data structures, that's a major effort, right? You pretty much, the question is, what is the like main principles for these data structures? Lean MLIR provides SSA and all these kind of formalizations for free for pretty much anyone of a developer. And again, having these kind of sidekicks where you just agree on the very basic data structure that you want, I think is what as a community can give us a lot of synergies. Thank you.